So the first thing that I want to show you is that you want a compliant solver. I'm gonna show you why in a moment. So you need the input to be NLP abstract NLP model. But if you want a compliant solver, you also need the output to be specific, and it needs to be specified by SolverTools. So when I use SolverTools, I have a generic execution stats. There it is. I have a generic execution stats. And the mandatory arguments are a symbol, which is the status, which is also called exit flag, and the NLP. So it's the symbol and the NLP, which is the second one that we want. So first, which is the status in this case? So we have two situations. We either solve the problem. So if solved, the status is first order, or it hasn't solved the problem, and in this case it should be tired. And I'm gonna check if the maximum amount of time has been achieved. If it hasn't been achieved, that's because it has achieved the maximum evaluation. So I have if solved, it is a first order. If otherwise it is tired, it's either max time or max eval. Otherwise, I don't know what happened, it's unknown, okay? So it shouldn't be unknown, but just in case, never know what happens. So these are the two mandatory arguments, status and NLP, and I also gonna provide these other arguments, which is the solution. These are keyword arguments. So solution is X, the objective value f of X, the dual feasibility, which is the norm of dual, the primal feasibility, which is the norm of primal, number of iterations I haven't computed, so I'm gonna ignore for now, the elapsed time, which is delta t, and a solver specific function. So this hasn't been updated yet. This is a work in progress. It should have a multipliers output as well, and a solver specific dictionary, which in this case we're gonna set the multipliers to be y. So in the release version there is an open issue that this should change to multipliers instead of being a solver specific feature. The multipliers are gonna be mandatory. So this should be compliant. This is an output compliant with our JSO packages. So the status and the NLP, so the exit flag, if you want to call it that, and the NLP. The NLP is here so we can get the counters automatically. Solution, objective, dual feasibility, primal feasibility, elapsed time as well, and I only haven't put the iteration here. Since I'm gonna show everything, why not put the iterations? I'm not gonna use the iterations to stop our solver, because the evaluations already do that. When I use an generic execution stat, I always say output equals SQP. And instead of checking this, I can check output dot everything in here. I think I have a print output, which shows a lot of information as well. So the status is the first order stationary. Objective value is a number. Primal feasibility is a small number. Dual feasibility another small number. Solution is here in 4 iterations and 0.08 seconds of elapsed time. And solver specific multipliers are minus 1.015. Okay, so there is a catch here, which is the status has to be one of a set of allowed statuses, which can be found using those statuses. Okay, so this is the set of allowed statuses. First order is going to translate to a first order stationary. Max eval is going to be the maximum number of evaluations. Max time is going to be maximum elapsed time, and so on. If you made a mistake here, for instance, first order, and you run, is going to say this is wrong, and it's going to say the status first order is not a valid status. Use one of the following, and it prints the list of allowed states. So this is a compliant solver. Before showing why do we want a compliant solver, there is something else that you usually want to do, and this something else is to print the report of this solver. So we use logging and a SolverTools function, which is log header, and I think I have to say info log header is gonna be call names, which columns I'm gonna show. I'm gonna show the iteration, I'm gonna show the objective function, I'm gonna show dual, I'm gonna show primal, and that's it. And which are the types of these things, so we can format it pretty. This is an integer, these are floats, okay? I can use a HDR override, which is a header override, to change the name of these arguments. Header override. fx should write f of x. So essentially a pretty printing. Dual should write nabla lxy. And primal actually vert. And primal is gonna be the vert c of x vert. So this can be deleted. Log row, the first row is gonna be, I'm gonna set any iter f of x dual and norm of primal. Be lowercase, and here in the end as well. So here it is. It doesn't print so well in the notebook as well, but this at main in66 should not be here in the terminal. Should be a lot better. So iter f of x, the norm of the Lagrangian, the norm of the constraints function. 0, 1, 2, 3, 4, and so on. Okay. So these log row and log header functions are used to automatically format this output. Also, you can pass some arguments to change the format of these columns individually. I'm not gonna do now. So this is the basics. These are the basics. Let me stop again. So these are the basics of creating a solver. Now we're gonna test the solvers on some problem. So I'm gonna first create some problems. Since I don't want to open any list of problems now, I'm just gonna create some fake problems so we can get on with it. And the list of problems is gonna be a list of fake problems, ADNLP model, which is gonna simply be the function I times x1 squared plus I plus 2 times x2 squared. I'm gonna start at point 122. I'm gonna start point 112, and my constraints are gonna be simply I times x1 minus I plus 3 times x2. So this is gonna be an easy problem. I actually gonna change something so it isn't so easy. x2 minus ix1 squared. So kind of Rosenbrock like I'm missing some, no. For I equals 1 to 5, okay? So just so we check that this is working. Oh, this actually should be a generator, not, it doesn't have to be a generator, but it can be a generator. So objects of type array are not callable here. Say goes for NLP in problems, output equals SQP NLP, print output. So we are running our NLP in several problems. Okay, this is cool. This is printing everything. But I want to automatically run these problems here. I'm going to use solve problems from SolverTools to solve these problems. I'm going to say solve problems. It should be the solver and then the problems. I can set some additional options as well. The solver is SQP and the problems is the list of problems that I have up there. When I run solve problems, it runs the problems. It says the names of the problems here, which we can fix. Number of variables, status, time, everything like that. And it prints a data frame with that information, okay? So this is useful because when you have a solver like a solver that is NLP models compliant, you can pass it to solve problems and it automatically runs and gets a data frame with the results. There are 31 columns here of information. I'm only seeing 9 columns, which is the ID and another columns. And you can see that I have the status here, the objective, the elapsed time, everything that you need to compare these solvers, okay? When we have more than one solver. To name our solvers, prob I. So there we have it. Prob I are now being named. Prob 1, 2, 3, 4, 5. So now that we have our solver working and we have it tested on some problems, we can print this information. So I'm gonna save it inside stats. And we're gonna use SolverBenchmark to write this information to some formats that are useful for us. We have markdown table in which you can pass the IO, which in this case is going to be just a standard out, the stats, and you can say which columns do you want printed here. So let's say, for instance, I want the name, the status, the objective function, the elapsed time, and I could have dual and other columns. I simply write down markdown table, enter, and it prints a table sufficiently well formatted so I can just copy paste in a README, for instance. So let's test here in a markdown format. It's pretty. Okay, so it looks good. Another situation that is also very common is a LaTeX table. So if you write down LaTeX table, this is gonna print down a long table, which is useful if you have like hundreds of problems and you don't want the page break to destroy your document. So you have a long table with name, status, objective, elapsed time. Notice that the underscore is corrected, and it is also well formatted here, okay? The LaTeX table function will provide you with a LaTeX document easily, okay? With these functionalities, you have, in a very easy way, you can create a solver. If you use NLP models and SolverTools to make it compliant, you can then use SolverTools to run your problems on it, and then you can use SolverBenchmark to write a LaTeX table with the result. So it's a very expedited pipeline of writing a solver and writing the paper that goes with the solver. Okay. Of course, if you don't want the paper, that's also good. You're gonna have a very quick way to write a solver. And since we have many solvers that accept, or we have a few solvers already working that accept the input and output to be JSO compliant, you can compare these solvers as well. Okay. So in our case, we have a simple SQP method that we could compare against IPOPT, for instance. I'm gonna have to install IPOPT, so let me just IPOPT here. So I have installed IPOPT. I had to make a new release that was compatible with NLP Models 12. So I have IPOPT 032 here. So I'm gonna use NLP Models IPOPT. And since IPOPT through our NLP Models IPOPT wrapper is compatible with the JSO packages, I can just call IPOPT NLP. So, yep. So here is the IPOPT output as usual, and print output is gonna print the same information that we have provided for our SQP solver. It has a status, objective value, primal and dual feasibility, solution, and so on. So IPOPT has been wrapped in this compliant solver, and I can call solve problems IPOPT problems. Okay, it's gonna work the same way. It's gonna print a bunch of things here. Don't worry about that. And now for the fun part, I want to compare my solver and IPOPT. So I'm gonna create a solvers dictionary in which I'm gonna name our solvers. So my solver is SQP and IPOPT is IPOPT. But since IPOPT has some options that I want to change, I'm gonna define anonymous function here, just so I can pass print level equals 0 to IPOPT, so it doesn't bother me with this long logging of information. And I'm gonna say df equals bmarked solvers, which is benchmark solvers, our solvers and the problems. So this is the result, a dictionary of symbols and data frames. If I say df SQP, is gonna show that same SQP I had, and df IPOPT is gonna show the data frame that I have if I call solve problems with IPOPT. Okay, so these two guys can be joined. So I can create the df join by saying let's write SolverBenchmark.join to make sure that I'm not breaking anything. Yep. And now which columns I want to join this. So now I'm looking only at the objective and elapsed time of both IPOPT and SQP. You can see here in the name of these columns. And I can say that I want more information here. I have prob1, prob2, and so on. I can write invariant columns. And I can say that the number of variables, the number of columns are invariant, that they should appear here for this. I don't need to create an nvar IPOPT and ncon IPOPT. It's just one nvar and one ncon. The name, the number of variables, the number of columns, and ask it to write for me everything that I need. Okay, so our pipeline of developing an optimization problem. You define your solver using NLP models as input, generic execution stats as output. You use SolverTools to benchmark your solver with other compliant solvers. You use SolverBenchmark to print your results, your comparison, your tables in LaTeX format. The only thing missing now is using benchmark profiles to create performance profiles. Okay, so this I'm gonna leave to a future episode of our tutorial. Okay, thanks for watching. Please subscribe and follow me on Twitch as well, so you can participate in our live tutorial sessions. See you guys next time.